Hello everybody, in this video I will build and train a very basic score entropy diffusion model that is capable of generating human-like tests using a very small dataset. I'd also provide the Colab notebook for you to play with. So traditional diffusion models has achieved a great success at image generation, but applying them to discrete data, like for example using them to generate text, has been a challenge. While autoregressive models like ChatGPT are the popular methods used right now for text generation, they also come with some limitations, like for example the sequential sampling, where you need the current token in order to generate the next one, and then you need the next token in order to generate the one after it, and so on and so forth. So you cannot make this in parallel. Those models are also difficult to control and usually require complicated techniques like, for example, temperature scaling in order to generate high quality output. Score entropy diffusion models introduces a new alternative method to model discrete data, like for example, text generation. So according to the paper, those models has got the potential to produce faster sampling, better generation quality, and flexible and controllable outputs. So right now, for example, instead of having to generate the text sequentially, you can just start at any part of the paragraph and generate the rest. So this work is based on the paper Discrete Diffusion Modeling by estimating the ratios of the data distribution. All right. By the end of the video, we'll also derive the loss functions and explain some of the equations used in the paper. Let's first explain the basic idea behind the diffusion models in general. Okay, so first we say, since we have a lot of data, for example, we have a lot of images, why don't we extract patterns from those images and then generate more variations based on those patterns? Okay, so let's assume that we have a huge number of data. Okay, we want a mechanism in order to be able to extract patterns, general patterns from those data, and be able to generate more variations based on those patterns. So, in order to do that, we will use what I call the diffusion trick. The diffusion trick is the foundation behind the diffusion models. So, what is the diffusion trick? If we look at those two images, we have this original image, and then we have added some noise to this image. So, what if we have trained the model to step back from this image into this one? So, we will give the model both images, and we will train the model to generate this image based on this input image. All right, so what if we did that once again? What if we add even more noise to this image into a third image over here, and then train the model to step back from this image back into this one? And what if we also did that again to this image and added some even more and more noise into a fourth image and trained the model to step back into this one, and then back into this one, and then back into this one? So we have trained the model to crawl its way from chaos into order. The more steps it goes through, the more order we get. So this is the basic foundation behind the diffusion models, and this is our trick in order to be able to extract patterns from those images and generate new different variations. Because right now, we will give the model some random noise and it will keep crawling its way until it gets to an order. So it will transition from chaos to order. All right, so let's sum up our strategy. We bring some original data set, and then we add noise to that data set, and then we train the model to get back from the noise into the order. And we do that once again, and again, and again. Now each transition is called a step. So now that we have understood the idea of diffusion in general, let's talk about discrete diffusion. In the case of discrete diffusion for text generation, we will be changing words instead of changing pixels in an image. For example, we apply noise on the sentence by changing some of the words. For example, the word the remains the. The word cat changes to dog. The word sits changes to jumps. The word on remains on. The word the remains the. the words mat changes to rock. And right now, we will train the model to get back from this sentence into order, which is this sentence over here. But why do we call it discrete diffusion? What is discrete about it? All right, in order to understand that, let's do the following. We will give each word in the dictionary a number. So, for example, the word the, we will give it number 1. The word cat, we will give it number 2. Okay? The word sit, we will give it number 3. The word on, we will give it number 4. The word dog, we will give it number 5. So this is our dictionary. Every vocabulary will have a number. So whenever we are trying to predict the next sentence of the next step, we will be predicting discrete values instead of kind of like a continuous range of values. So for example, if we are at this step over here, our next prediction will be, for example, 1, 2, 3, 1, 5, 1. Okay, so this is a discrete prediction. But the classical diffusion is designed to predict a continuous range of values rather than discrete values like those. So we need to find a way around that. So one might suggest that we can train the model to predict the next word by predicting a continuous range of values, like for example, predicting a value between 1 and 10, and then we can discretize that into the closest discrete value. So let's say that our model predicts a value between 1 and 10. All right. Let's say it comes up with a value of 6.3. So we can discretize that into 6 and say that the model has predicted the value 6. All right. So this can be valid if we have a low dimensional space, like this case scenario where we have like one dimensional space between 1 and 10, or in the case of images where we have a range between 0 and 255. But what if we have two-dimensional space? This is still easy. All right, what if we have three-dimensional space? Okay, this is getting a little bit more complicated, but it's still possible, right? What if we have four-dimensional space? What if we have 20-dimensional space? What if we have 50-dimensional space, right? So in the world of transformers, okay, we have a very high dimensional space, which makes the discretization process very hard and impractical. We need to find another way of doing it. So our first very simple way of doing it was about simply training the model to predict continuous values and then try to discretize that into the indices of the predicted words. And we have found out that this is very impractical because it's very hard to discretize a very high dimensional space, like the space of the words. So again, let's redescribe our situation. We are trying to train the model to get back from this noisy step into this less noisy step over here. All right. So the input of the model is the indices of those words. So we told the model that we have the word 1 and the word 5 and the word 3 and the word 2 and the word whatever. All right. And right now we are trying to design the output of the model. So our first suggestion was to predict the indices of the next less noisy step over here. And due to the fact that it's very hard to discretize
a very high dimensional space like the space of the words, we found that this is impractical. So what do we do next? All right, we can do something smarter. Instead of predicting the indices of the next words, we can predict the probability of the next word. All right, so assume that we have a vocabulary of 10 words. We will predict the probability of each one of those 10 words for this position over here. And we will predict the probability for each word in the vocabulary at this position, and this position, and this position. Now, the beauty about the probability is that it does not have to be discrete. It can be continuous because all the mechanisms in the diffusion process are continuous. So, in this way, we can work with continuous values, no problem. Right, that sounds like a great idea, but we have a remaining difficulty. If we are going to be predicting the probabilities, all the probabilities for a certain position among the vocabulary, we have a condition that should be satisfied. The condition is that all those probabilities should sum to 1. All right, so we say 50-50, right? Because so if we say we have a 50% chance that you will win and 50% chance that you will lose, the probabilities should sum to 1, right? You cannot say you have a 50% chance you will win and a 70% chance that you will lose, right? So the probabilities for all the vocabulary at a certain slot in the sentence should all sum to 1. And practically it's very hard to train the model to generate probabilities that sums to 1. So training the model to generate probabilities while at the same time all the predictions summing to 1 seems to be an impractical thing to be done, which is why we come up with a new idea. Alright, so why don't we predict the ratios between the probabilities of the vocabulary at a certain spot? So instead of predicting the probability of each of the vocabulary at a certain spot, why don't we predict the ratios between those probabilities? So why don't we say the ratio between the first word and the second word is something. The ratio between the first word and the third word is something. The ratio between the first word and the fourth word is something. The ratio between the second word and the rest of the word is something. The ratio between the third word and the rest of the vocabulary is something. So this is what this paper will do. It will predict the ratios of the probabilities at a certain spot instead of predicting the absolute probabilities.
All right, in order to better understand the structure of the model, let's have the following simple example. In this example, the model will predict a sentence, and the sentence consists of 3 words. Okay, so just like normal diffusion models will predict images or an image, this model predicts a sentence with 3 words. Okay, so in our situation here, we have 3 words, and each word has got an index. Okay, for the simple example. For example, the word I has got the index 1, the word like has got the index 2, the word dogs has got the index 3. Now, the model will have a dictionary of words, which are the vocabulary that the model works with. So in our case here, for simplicity, we only have 3 words. Okay, so the model only works with 3 words, which are I, like, dogs. Now, for each slot of the sentence, we have what we call a probability distribution. What is a probability distribution? The probability distribution is the probability of each word from the dictionary to appear at this particular spot. So, for example, we have a probability of 0.1 for the word dogs to appear at this first slot of the sentence. We have the probability of 0.5 for the word I to appear at this slot of the sentence.
and we have a probability of 0.4 for the word, for example, like, to appear at this slot from the sentence. Okay, and for example, we have a probability of 0.7 for the word like to appear at this slot from the sentence. Okay, and for example, a probability of 0.4 for the word dogs to appear at this slot of the sentence. So now, instead of trying to predict those probabilities directly, okay, for example, giving the model the indices 1, 2, 3, and it will predict that those are the probabilities that we have over here. Okay. Instead of doing that, we will predict the ratios between those probabilities. So instead of predicting 0.1 for dogs, 0.4 for like, 0.5 for I, no, we will predict 0.1 over 0.4. Okay, so we will say that the probability of the first word from the vocabulary over the second word from the vocabulary is, for example, 0.1 over 0.4. Okay, the probability of the first word from the vocabulary over the third word from the vocabulary, for example, is 0.1 over 0.5. Okay, so in this way, we will be predicting the ratios between the probabilities of the word from the vocabulary instead of predicting the absolute probabilities for each word from the vocabulary to appear at a certain slot in the sentence. All right, so now once you understand this, you will understand the structure or the basic structure of the model. So we have a model. Okay, we have this pen. If I'll try to draw something. So what is the input to this model? The input to this model is the indices or the vectors for the words of the current step. Okay, again, let me remind you that we are trying to denoise the sentence and get back from noise to order. So for example, at this step, we have the input of 1, 2, 3. Okay, so we're telling the model that right now we have the sentence that consists of 1, 2, 3. Okay, what will the model right now predict? It will predict the ratios that we have talked about. Okay, it will predict those ratios. All right, but one very important thing that I should point out over here, this is, let's say, t plus 1, okay, step. So right now we have two steps. This is a noisy step over here and the original step over here. Okay, so it was I like dogs. We added some noise right now to the sentence, so it became I dogs dogs. Okay, now very important thing that you should understand in order to understand the structure of the model, which is the following. The input of the model will be from t plus 1, right? Okay, so right now we are here and we want the model to be able to predict getting back to here. Okay, so the input to the model will be from t plus 1. So the input to the model will be, for example, 1, 3, 3. Okay, those are the indices of the words inside this current sentence at t plus 1. Okay, so the input to the model will be from t plus 1. Now, the output of the model will be those probabilities from t. Okay, so the ratios between the probabilities for the vocabulary words at each slot will be at time t, okay, and the indices for which describe the current word in this kind of like noisy step will be from t plus 1. Now, a lot of kind of YouTubers or some people that try to explain the EDD will say that the ratios are from t plus 1 over t. They say that the probability ratio is t pt plus 1 over pt. This is not true. Okay, this is a mistake. Okay, the ratios will be, if you look at the paper, the ratios will be from the same time step. Okay? But the input to the model, which are the indices or the vectors describing the word of the noisy step, which we are trying to come back from, are from t plus 1. All right, assume that the model is able to predict those ratios. What can we do with those ratios? How would we use those ratios to make the backward step? All right, let's have a sneak peek of the next part over here. All right, over here, we have a very important formula. Now, this formula is the foundation for performing the backward step. Okay, this matrix over here will be used to perform the backward step. Okay, now the nice thing is that we can evaluate this matrix by multiplying those ratios which we are predicting by the Q matrix. And I will tell you what is the Q matrix. But this is like a sneak peek into how we will be using those ratios. So we will be using those ratios to evaluate a matrix that is needed and the foundation to perform the backward step. All right, good. So we understand the basic concept, and right now we want to, train a model. Okay, so we understood that the basic foundation for stable diffusion is starting with ground truth data and then adding gradual noise to those sentences, okay, in order to get some more noisy sentences, and then training the model to get back from the noise into the order. But how do we exactly add noise? How do we practically add noise? So okay, we got it. Right now it was I like dogs, and when we added noise, it became I dogs dogs. But how do we practically do that? All right, if we remember that each slot in the sentence had a probability distribution for all the vocabulary that the model worked with. Okay, the process of adding noise is actually the process of changing this distribution. Okay, so for example, over here it was 0 0.1, 0 0.3, 0.6, it became 0 0.2, 0.2, 0.6. How did this change happen? We have multiplied this probability distribution by a Q matrix, by a matrix that we call Q. Okay, so this matrix will define how the noise is gradually added throughout the steps, and we call it the Q matrix. So by multiplying each probability distribution at each slot by this Q matrix, we get a new distribution. Okay, but what is that based upon? Let's have a look at the mathematical foundation for what we are actually doing. So one very famous mechanism to add noise in the diffusion process is using what we call the Markov process according to this equation over here. It says that the change in the probability distribution equals the multiplication between this Q matrix, which we have mentioned right now, and the original probability distribution over here. And just like any first order differential equation, we can approximate it by saying that the change in PT will equal delta T times QT times PT, right? So it will be delta T times QT times PT. All right, so in simple terms, we say that the P new, the new probability distribution, will equal the P old plus delta T times Q times P old. All right, but wait a minute, wait a minute. Assume that we have this original distribution and we have multiplied this distribution by QT, okay, or Q delta T, and we got this new distribution. Okay, very nice. Assume that I'm a very beginner in probability. How did we generate this word over here? All right, and this is what we call a stochastic variable. So there are a lot of methods to generate the specific token based on the existing probability distribution. But Okay, one very simple way of doing it is the following. Let's assume that we have this range between 0 and and 10. Okay, so we will generate a random number, okay, between 0 and 10. Okay, so we will say, based on this current distribution, if the random number is between 0 and 3, then it will be the first word. Okay, if the random number is between 3 and 6, okay, which is this 30%, it will be the second word. Okay, if the random number is between 6 and 10, it will be the third, okay, word chosen. Okay, so we will reflect this probability within our random generator. So this is the mechanism that I'm gonna use in the code, in the demo code, in order to sample those tokens based on the newly generated or modified probability distribution in the next noisy step. All right, let's dive into finding Q inverse once again. Let me remind you again, what are we talking about over here? So, if we want to find the element in Q inverse that corresponds to the transition between Y and X, and by Y and X, we mean two different potential words in the dictionary, right? Okay, so for example, this corresponds to the word the, and this corresponds to the word car or whatever, all right? Okay, so if we want to find the element in Q inverse that corresponds to the transition between the two potential words Y and X, we will multiply the probability of the word Y over the probability of the word X by the element in Q that corresponds to the transition from X to Y. The other relationship, if we want to find the element in Q inverse that corresponds to X remaining as is, we will sum all those elements over here. Okay? So right now I will show you an example. All right. So in this example, this is the QT. Okay? And we have multiplied this QT by the probability distribution vector, and we have got this transition over here. Now, this is the Q inverse. So right now you can start familiarizing with the concept. And once we multiply this Q inverse with this same probability distribution, we got the opposite of the vector. Okay, so if this vector has gotten us kind of like in this direction, okay, this vector will get us in the exact opposite direction. So it will reverse the effect. All right. So how did we practically find this Q inverse over here? Instead of looking at those kind of like complex relationships, let's have this practical example over here. How did we get this element? We had divided this probability over this probability and multiplied it by this element over here. How did we get this element? We have divided this probability over this probability and multiplied it by this element over here. Okay. How did we evaluate this one? Okay, we have divided this over this and multiplied by this. Now for the diagonal, okay, where the probability of the element remaining as is, okay, in the second relationship, we will do the summation which we have talked about. So if you focus on this slide, you will be able to completely understand how to apply the formula in order to be able to evaluate Q inverse from Qt. All right, okay, again, let's focus on the second relationship over here, which is evaluating the probability of the token remaining as is, which represents the diagonal, okay, in the matrix. So
in order to find this diagonal elements over here, okay, we will sum all the elements, all the other elements in the row, okay, and add a minus sign. So 5 over 3 plus 2 over 3 equals 7 over 3 with the minus sign, okay. In order to find this element over here, we will sum this and this with and add a minus sign. 3 over 5, 2 over 5 will equal 1 with a minus sign. And similar calculation in order to find this element. All right, so getting back to our forward diffusion formula, using the Euler formula, we said that the new probability distribution will equal the old probability distribution plus QP times delta T. All right, so since we said that this is going to be the exact opposite once we change Q to Q dash, we can rewrite this formula as the following. Pt plus 1 will equal Pt minus Q dash Pt delta T, right? Okay. Do you remember? Okay, remember when we said that using the opposite or the inverse matrix will result in the exact opposite vector, right? So we just substituted that and reversed the sign over here. All right, now maybe we can get Pt out, okay? So we can write I minus Q dash delta T times Pt will equal Pt plus 1. So right now, this is the formula that we will be using in order to find Pt based on Pt plus 1 and the predicted ratios over here. So this is the formula that we will use in the reversed diffusion process or to find the reversed step. So we have Pt plus 1 and we have the predicted ratios which will allow us to evaluate the Q dash, and then we will be able to find Pt. Now, this is the loss function, which will be used to train the model that will predict the ratios, okay? So this is the loss function that is suggested by the paper. The formula might look scary, but it's actually very simple. Now, those are the ratios, okay, that we were always talking about. And this is the neural network that will predict the ratios. Okay, so this is the neural network or the model that we will train to predict the ratios. It's at the heart of this loss function over here. Now, this formula might look scary, but it's actually very simple. It just means that this model, this score function model, this neural network that we have trained should actually predict those ratios over here. So the closer the output of this model to those ratios, okay, the closer to zero this whole term will go to, which is what we want. Okay, so this whole term, which is the loss function, is actually like the error which we are trying to eliminate, right? So this whole term should actually go to zero if we are doing proper training. So once this model starts to equal to those ratios over here, this whole term will go to zero. And I'll show you why. So right now, if I substitute for each term, S term, Py over Px, okay, minus this whole same term, Py over Px times log Py, okay, over Px, okay, plus k. What do we mean by this k function? This is the meaning of it. It's over here. It means a times log a minus 1. So if we substitute that, it will mean Py over Px times log Py over Px minus 1, right? So if we look at this whole term over here, I know, sorry, okay, the writing is ugly. I'm just getting used to the pen over here. But this means if we do the calculation, we will find this whole term goes to zero. Okay? So this one will go with this one will go with this one will go with this one, and whatever. Okay, so this whole term will go to zero. So in other terms, all right, this formula looks complicated, but it actually just simply means S should equal Py over Px. Okay? All right. Now I want to go for the demo code. So I'll go to colab.research.google.com and I will go to File and upload the notebook provided. Okay, it is in the demo notebook folder. Okay, it's this one. Now this one, if you want to see all the work and the code and the research and the struggle I've gone through, you can have a look at this code. It's kind of like a long notebook that includes a lot of work and trials and research and stuff. But the final residual outcome is in this notebook over here. So I will upload it. And here we go. So in this demo code, we will have an example data set. So I have a group of sentences over here that I want to train the model for. The next step is to generate a dictionary. Okay, so what this code will do, it will take each distinct word and give it an index. For example, okay, it will take the word I and it will give it number 1. Okay, it will take the word like and it will give it number 2. It will take the word painting and it will give it number 3. Now, if it gets back to the word I, it will not consider it because it has already registered it. So it will go for the next word and give it number 6, and so on and so forth. Okay, so in this way, we have generated the dictionary in order to be able to work with the words. So right now, I have run this set. I have defined those sentences over here, and I have run this dictionary. So let's have a look at the output. It says that, the word I is number 0, the word abroad is number 1, the word adore is number 2, the word adventures is number 3, and so on and so forth. So right now, according to this dictionary we have created over here, we have indexed all those sentences in the data set. So we have this outcome over here. So the first sentence is 0, 41, 57, 31. The second sentence is 0, 23, 13, 43, okay, and so on and so forth. So in our vocabulary, we have 94 words. So in the next step, we will generate the training data. So we'll generate training data in order to train the model to predict ratios. Now let me go ahead and remind you of the structure of the training data. What is the input? What is the output? Let's go ahead and remember that. All right, in order to remind you of the structure of the training data, I have recreated this example which we have explained before. So we have the ground truth. We have the ground truth sentence over here, okay, which is I like dogs. Okay, now we have performed forward diffusion and added noise to this sentence, and we got right now the sentence I dogs dogs, which is the noised sentence. And right now we want to train a model that to get back from this noise sentence into the original sentence over here. All right, so we want to train a model that takes the input from of the indices of those words, like for example 1, 3, 3, and it should generate the ratios
of those probabilities over here. Okay, so the input to the model will be the indices of the next step of the noisy step, and the output of the model will be not those absolute probabilities, but the ratios between those probabilities. So our model will give me zero point 0.1 over zero point 0.5 ratio, the 0.1 over zero point 0.4 ratio, the 0.5 over zero point 0.1 ratio, the 0.5 over 0.4 ratio, okay, and the 0.4 over zero point 0.5 and the 0.4 over zero point 0.1, and the same for the other two words over here. So the input to the model will be the indices of the of the words in the step t plus 1, and it will predict the ratios at the step t, okay, and then it will use those ratios to construct the reverse Q matrix, and it will use that Q matrix and this probability distribution to generate the probability distribution of this previous step over here. And then it will use those probabilities in order to sample the new sentence of the previous step, which is closer to the original uh, sentence. All right, so this is how we'll be working. We'll be bringing our ground truth sentence over here, adding noise to it, and from the new probability distribution, we will sample this new noisy sentence over here. So we will have those indices and the ratios of those probability from a previous step, and this will present one training sample for our model to train on. Okay, and then what we will do right now is we will do this noising part once again for one more step. Okay, for t plus 2 right now. Okay, and this will generate new indices. Okay, let's say 1 1 3 whatever. Okay, and right now we will train the model based on those new indices to generate those ratios, okay, over here from this previous step. Okay, and we will do that once again and once again for 10 steps, 20 steps, whatever. Okay, so we have done it for this part or for this sentence, and we will do right now this for the next sentence and the next sentence and the next sentence, right? Okay, so those are the training samples for our models. All right, let me show you the part where we add the noise to the sentence in our function. This is the Euler formula. Okay, so this is PT, the original probability distribution, plus delta T times QT times PT. All right, so this is the forward diffusion process where we add noise to the sentence. Now this function over here will take in the probabilities and compute the ratios. Now this function over here will sample the tokens based on the existing probability distribution, okay, using the random choice method which I have explained before. All right, so right now we have run this code and generated the training data. Let me show you how does it look like. Let's print extreme. All right, so this is how the X train looks like. You know, it is the indices that we have talked about. So those are the indices of t plus 1, right? Now for each indices of t plus 1, we will predict the ratios of the probabilities at t, right? Now let's print the output, Y chain. All right, so this is, so those are, it's a little bit jammed over here. So those are the ratios, okay, that we have talked about. For each word, we have the ratios for each word in the vocabulary. All right, now this function over here will construct the Q bar matrix, which is the inverse matrix used in the reverse diffusion process.
And again, if you remember back in the videos, I have explained the backward diffusion equation over here, where we will construct the PT from or using the PT plus 1, because right now we're getting back from the noisy into the original, right? And this is the equation. And this is the equation that I have explained and derived in the previous videos. So right now, we will train the model. So we will have our X train and we will have our Y train, which I have showed you before. And we will train this model. We will make sure that we will normalize the output and we will create this simple model, few layers over here. And we will use this preload activation function and a linear activation function at this layer over here. And we will use the Adam optimizer and the mean square error. Very simple, nothing complicated, very simple model. All right, after training, we will run this cell just to define those functions. And again, this is the function that reconstructs the Q-bar matrix based on the ratios, okay, which are predicted from the model. And we have exactly explained how to do that mathematically. And this is the backward diffusion process that we have also derived before. I guess I've talked about that. All right, now before we go to the fun part, which is generating new sentences with the model, I have just made one quick modification. So I have changed how we design the Q matrix. So as you know, the Q matrix is a question of design. You know, you design it in a way, a different engineer will design it in a different way. So the Q matrix will define how the noise is added to the original sentences and how the noise is scheduled to be added across the steps. So when I was using this code over here, the noise was being added very fast in the initial steps. So this caused the model to keep flipping. Every time it reaches a meaningful sentence, it flips back into noise at the next step. And now I will tell you why. So what I have done is I have changed this model for the QT and I've just used this simple code over here, okay, to generate the Q matrix. And I will show you how it looks. This is how it looks. Very simple Q matrix. So when I use this Q matrix, the beauty about it is that the initial added noise started slowly. So if you look over here, this is the first step of the first sentence. This is the second step at this sentence. Once some noise is added, you know, most of the words did not change over here. And then this is the third, and this is the fourth, and so on. So most of the words did not change on those initial steps. All right, so this slow addition of the noise across those initial steps tells the model the following. It tells the model that once you reach something good, once you reach something meaningful or human-like, just slow down, don't change, right? Because this is what we train the model for. We train the model to generate this sentence from this one, right? We train the model to generate, you know, this step from this step, okay? So, and kind of like this step from this step, right? We train the model to get back, right? So once we introduce slow noise in the beginning, we are telling the model that, you know, if you have something human-like, you know, slow down, don't change a lot, okay? Let me give you an example for this to understand what I'm talking about. Now, this sentence over here is exactly the original sentence, okay? Or maybe let's look at this one, sorry. Okay, now this sentence is exactly the same as the original sentence, the one that we have started with. Okay, so here's what we will train the model for. We tell the model that once you reach this type of sentence, just don't change. So look at the next step or the previous step, which the model will be trained to generate. It's the same. So it's kind of like telling the model, once you reach something like this, something cool like this, just don't change. Okay, just stay where you are. Okay, so this is the beauty of adding noise slowly in the initial steps. But if we added the noise very fast, then the model
would not know what to do once it reaches something meaningful. So it will reach something meaningful, and then once you make one more step, it will step or flip into back into chaos. And this is what was going on with me. It will reach something meaningful, like, for example, I like driving cars, and it will flip back into noise, into something meaningless, and it just will keep flipping. Okay, why? Because I was introducing the noisy steps very fast. So let's assume, for example, that I have started with this initial sentence, and then every word over here in the next step changed. Okay, so in this situation, the model would not know what to do once it reaches this one, because it was not trained. Okay, it was not trained for anything to be done once it reaches this order. Okay, there's no training, it doesn't know what to do next, right? So if we just directly changed everything fast from this meaningful sentence into noise, what will happen is that the model, once it reaches this okay, this order or something similar, it will not know what to do. Okay, because there's no training over here, there's no step before this one. Right. So whenever there's no training, or the model is working in a space, okay, with no training, it will just malfunction. So what was going on with me is that the model will reach a meaningful sentence, and then it will flip back into chaos. Okay, and then it will reach a meaningful sentence after a few steps, and then it will flip back. So there was no stability. All right, now let's generate something. Now this function over here will generate random probabilities. It will just generate uh, some random probability distributions, and consequently random initial sentence to begin with. Okay, it will be just a bunch of meaningless words. Okay, so we will run this cell. Okay, and right now, every time we run this cell, it will move one step backward. Okay, yeah. So starting from that noise, we have start. Okay, right now, one step we have reached this. Okay, let's do one more step. I enjoy painting nature. Wow, that's amazing. Okay, so I enjoy painting nature. I practice dancing trips. Okay, that's nice. Okay, so let's start with another initial random step over here. So again, let's start with something meaningless, because this is just the first backward step. I enjoy playing daily. Wow, I'm super impressed actually by how this model works. Why am I so impressed? Because I've just um I have just trained this model with those very, 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 very few sentences. Okay, nothing big. I did not, training in kind of like 100,000 sentences, or kind of like 5 million sentences, and, millions of weights or anything. So that really proves that, there is something to this, discrete diffusion. It's really, 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 really super powerful. It's really generating some amazing. I've tried it many, many times. Okay, it's really generating something really, really, really meaningful. I adore exploring poetry. Look at this. I adore exploring poetry. That's amazing. I enjoy watching trips. That's also meaningful. All right, I've got another really, really beautiful combination. I love nature games. That's really great. And this is exactly what we want. What do we want from those models? We want those models to be able to extract patterns from the original data and give us all sorts of different variations and combinations. Okay. So frankly speaking, if we just have this very, very tiny little data set over here, and it was able to come up with all those beautiful um, meaningful combinations. So can you imagine if you have millions and millions of of training data? That will be a different story. So thanks so much for watching this, and see you on the other side. Just one last thing. Every time you want to start from the initial random noise, just you run the cell, okay, and then you start stepping over here. Okay. All right, so let's answer some questions. The first question is, where did this inequality come from? So, what is this inequality in the first place? So, we will rely on this inequality in our training, because in our training, we will be trying to minimize this negative log over here. So what we're doing in our training is trying to minimize this negative log likelihood over here. When we minimize this negative log likelihood over here, it means that this probability is bigger. All right, so let's understand what's going on over here. So P is the diffusion model that we are trying to train. Okay, it's the model that we hope it will be able to generate a human-like text. All right, now X naught is one sample of the training data. Okay, so let's assume that it's a sentence or an article that we hope our model will be able to generate something similar to. So, training the model is about increasing the probability that our model will generate something similar to this training data over here. Okay, so by training, we are trying to maximize the probability that the model will generate something similar to this training data. Okay, so we are trying to maximize this one. In other words, we are trying to minimize this whole term over here. Okay, so by minimizing this term over here, we are maximizing the probability that our model will generate something similar to this training sample over here. Okay, so let's be accurate about something here. Now, we call this the likelihood. Okay, so what is the difference between the probability and the likelihood? Okay, now this is a very interesting question over here. What is the difference between the probability and the likelihood? Are they the same thing? Are they different? So right now we have this. We have P of what? We have P of X naught. Okay. In other words, what is the probability that our model will generate X naught? Okay. So what's the difference between likelihood and probability over here? It's just a question of perspective, and I'll explain. All right, in order to understand this, let's look at the situation over here. Let's assume that we have already trained our model, okay, on our data, and right now we are evaluating P of X naught, okay, and we got like, let's say, for example, whatever, 0.6 or whatever, okay. So right now the model is already trained, and right now we want to see what is the probability that the answer will be X naught. In this situation, okay, the ground truth is our model because we have already trained the model, and right now we are relying on the model to generate the training to generate the probabilities. So we call it probability in this situation. Okay. Now let's look at this second case. Okay. Now let's assume that our model is not trained. We are still training the model. So still our model doesn't know anything. Okay. And the ground truth right now is the X naught, because right now X naught is part of the training data. Okay. So right now we are evaluating the model. We are not evaluating the possible outcome. Okay. So from this perspective, we are evaluating the model. So when we get this probability, let's say point whatever, 0.3, for example. Now in this situation, and from this perspective, we call it likelihood. Okay. So we say the likelihood of X naught is 0.3. All right. So in this situation, the data point is the ground truth, and we are evaluating the model. So we call it likelihood. Okay. In this situation, the model is the ground truth, and we are questioning or evaluating the probability of the data. Okay. So in this situation, we call it probability. In this situation, we call it likelihood. Okay. So right now over here, because we are training the model, right? We are in the process of training the model. So we will call it what? We will call it likelihood. This is why we call it likelihood training. Okay. So in the situation over here, by training, we are trying to maximize
the probability or the likelihood, okay, that our model will generate the training data, right? So let's assume that we have given it a sentence or an article, for example. We want high probability or likelihood right now, right? Okay, that our model will generate this article or this or something similar to this article. So if this value is high, then we have done the training, right? Okay, so now maximizing maximizing this means minimizing this whole thing, okay, because it's inside a log or a negative log or whatever. So overall, we are trying to minimize this whole thing. So if we minimize this whole thing, we will be maximizing this probability or likelihood over here, okay. All right, it turns out that evaluating this term over here is very difficult, okay. So without a lot of details, evaluating this term directly for our training process is very difficult. So we're going to have to find a way around that. So here is where we get to the concept of the elbow. Okay. Now, what if I told you that for reasons that we will describe later, this term over here is always bigger than this term over here? Okay, this is what this inequality is describing. Okay, so what if I told you that this term is always smaller than this term over here? And I am trying to minimize this. Okay, so if I minimize this enough, then I've already minimized the other side because the other side is always smaller. Okay, so let's say that this line is always below, or let's say that this line is always below this line. Okay, so if I bring this line over here, then I'm sure that this line is at least below this point. Okay, so instead of minimizing this side directly, okay, I can minimize this side over here and use it as my training, um, as my loss function. Okay, so I can use this side because it's easy and calculatable. Okay, it's easy to calculate and practical. I can use that and minimize it. So if I minimize it, I'm sure that I have minimized the other side. Why? Because the other side is always smaller than this side over here. All right, so our training strategy once again, because calculating this side over here is very hard, okay, undoable. And because we know that this side over here, which we will describe and derive right now, is always larger than this side, and I'm trying to minimize this side. So if I minimize this side over here, then I'm sure that I have right now minimized this side over here. Why? Because this side over here is always smaller than this side over here. Okay, so if I have this again, let's say it once again. Okay, if I have this blue line and I have this orange line, okay, and I have a law that says that the orange line is always below the blue line over here. So if I managed to bring this blue line over here, okay, then I am sure that the orange line is at least below this point. Okay, so it will be something like this. Okay, so my strategy will be to bring the blue line, because once I bring the blue line down, I'm sure that the orange line by law will be below it. So in other words, this is going to be our loss function over here. Okay, so we in our training process, we will be trying to minimize this loss function over here. All right, so how did we come up with this inequality. In this video right now, in this part of the video, we'll explain how we ended up with that inequality because you were interested in that. All right, the first step is to understand that the probability that our model will produce x naught will equal this integration over here. But what does this integration mean? Okay, what do we mean by the p of x0t? Now, the probability of x from 0 to t, it is a path probability. What do we mean by a path probability? Okay, in order to understand the path probability, okay, let's have the following example. Let's assume that we have three words, which are A, B, and C, okay? And we have, let's say, two steps, okay? So, starting from the first step over here, so let's assume that the probability of C, let's say, is 0.1, okay? And then, based on that, the probability over here of, let's say, B, okay, is 0.3, just, okay? And then the third step, let's say we have three steps, the probability of A, okay, is 0.5, okay? Now, C, B, A, okay, is a path. So we call this a path. So right now, let's assume that we're doing backward diffusion, okay? And we started from C at this probability, B at this probability, A at this probability. Another path could be, let's say, C, C, C. This is another path, right? Okay, there are a lot of paths. Okay, another path is A, B, for example. Okay, so each one of those is a path. Okay, so if the probability of C was 0.1 and the probability of B was 0.3 and the probability of A was 0.5, then as you know that the probability of this whole path is what? Is the multiplication, okay, as we see in this formula, okay, is the multiplication of those three probabilities, okay? So it will be this one times this one times this one, right? So this whole path probability, the total multiplication, is what we call the path probability, okay? Okay, so let's back to our example. So we have ABC, okay, three potential words, okay, and we have just one word, okay, in our example. As in our sentence, we just have one word, okay. It could be A or B or C. So right now, let's assume that our A naught, okay, that we are trying to find the probability of, let's assume that it's A, okay. So we want to find the probability of A. What is the probability that our model, our reverse diffusion model, will generate A? Okay, so how would we evaluate that? Okay, what we will have, okay, so we have three diffusion steps right now. Okay, we have three steps, 1, 2, and 3, and we want the probability that the last step will be what? Will be A, for example. Okay, so what we have to do is the following. We will have to find all the possible paths along which we can go through, right? So we will okay, one path will be for example C, C, A, right? And the probability of this path will be what? will be the multiplication of the probability of each of those steps, right? Another one will be A, right? Another one will be B, 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 for example, A, right? So we're gonna have to go through all the possible paths that could end up in A, right? Okay, so in order to find the probability of having A eventually, we're gonna have to add them up, right? Okay, so let's assume that we have like 10 paths, all will end up in A, and the probability, for example, for each of them is, let's say, 0.1, the other path probability is 0.3, the third path probability is 0.2, okay, whatever, okay, 0.05, whatever, okay, I'm just coming up with numbers over here, okay, until we finish, for example, all the possible paths. So each and every one of those paths will end up with A, right? So what will be the probability of having A as the output of the model? It will be the summation, right, of the probability of each and every single path of those paths. So we will sum up the probability of all those paths because each one of those paths will end up with what? Will end up with A. So this is the intuition behind this integration over here. So this integration tells us to sum the probability of all the paths that ends up with x naught over here. Okay? So this is the intuition behind this summation or this integration over here. Okay? So right now we are done with our first step over here, which is to understand that the probability of the model generating x naught is integrating along all the paths that would end up in x naught, which is this integration over here. Okay? We call it the marginal probability because we have marginalized, for example, B and C right now in our example, and we have focused just on the probability of ending up with A. Okay? Very nice. All right. So what I'm going to do next for this integration over here is that I'm going to multiply and divide by Q of X from 0 to T. Or it's actually from T to 0. Okay? So what I'm going to do right now is I'm going to multiply and divide by this quantity over here. So I have changed nothing. I just multiplied and divide by it. Okay, so what do I mean by Q? I mean the forward diffusion probability. So let me remind you again, what do I mean by this Q? Remember that when we did the forward diffusion, we started with kind of like, let's get back to our ABC example. We started with kind of like 3 probabilities, right? Okay, and then we added some noise, and those probabilities has changed slightly in the next step, right? Okay, and then okay, and then in the next step we have added some more noise, right? We were multiplying by Q, if you remember. Okay, so this is the forward diffusion, right? So okay, so the probability of the whole path once generated by the forward diffusion, this is what we call Q of X from 0 to T. Okay, so the difference is this probability is generated by the model, okay, which we have trained, and this probability over here is generated by what? By the forward diffusion. Okay, so it looks like the ground truth, right? Very nice. So we have actually done nothing over here. We have just multiplied it, multiplied and divided by the same quantity over here. All right, so another way of writing this quantity over here is this way, okay? So this is the exact formula for the expectation of q of x from 0 to t of this quantity over here, okay? So we have arrived at the result or the fact that the probability that the model of the model producing x naught will equal the expectation of this quantity over here. Now, the Jensen's inequality tells us the following. It tells us that the log of the expectation of something, okay, will always be greater than or equal to the expectation of the log of something, okay? Okay, so again, the Jensen's inequality, it is a law that says that the log of the expectation of something will always be greater than or equal to the expectation of the log of something. It's more general than this particular case. Okay, the Jensen's inequality is actually more general than this. It says that the function of the expectation of x is always smaller than or equal to the expectation of the function of x, okay, if the function is convex, okay, and if the function is concave, it will be the opposite, okay. So in our case, the log of the expectation of something is always greater than or equal to the expectation of the log of something. Okay, I will also, if you want to understand more about the intuition behind this inequality over here, I will refer you to a YouTube video that you can watch in order to better understand the intuition behind this inequality and how it came about. All right, so we have gotten to the point where we know that this part over here is always greater than or equal than this part over here. But we have just derived the fact that this part over here is actually the log of the expectation, right? So we can rewrite that as what? Come on. Okay, so in other words, we can write that the log of, okay, the log of p of x naught, right? P theta of x naught, okay, is always greater than or equal to the expectation of the log of this quantity, right? Very nice. So if I add a negative sign, I can flip this out, right? I can write it in the opposite direction. Okay? So this is what we have reached right now and so far. So this part is what we have over here. Okay? And this part is what we have over here. All right. So this is the right-hand side. But wait a minute. Does this look like something? Does this remind you of something? Oh, this looks like the divergence formula. Okay? So the expectation of the log between two quantities is actually the divergence between those two quantities or those two vectors. Okay, if you're not familiar with divergence, let me go through it really quick over here. So let's assume that we have two vectors, vector A, again, and it's kind of like whatever, point one, for example, okay, and vector B is, for example, 2, 2, 2. So what is the divergence between those two vectors? Okay, so the divergence is kind of like the difference between those two vectors, the deviation between those two vectors. So we call it KL, sorry. We call it, for example, DKL. Okay, this is the type of the divergence, specific type. Anyway, again, between A and B. Okay, it will be. So what's the first thing that you will intuitively do? You will say 1 minus 2, 1 minus 2, 1 minus 2, right? Okay, yeah. But instead of subtracting those two quantities, we will take the log for this difference, right? Okay, so we'll say the log of 1 minus the log of 2. Okay, and we know that this, what does this equal? It equal the log of 1 over 2, right? Okay, by the law of logs. Okay, okay, one more thing. So we will say the log of this minus the log of this, okay, plus the log of this minus the log of this, the log of this, the log of this minus the log of this, okay, and we will sum the difference along all those elements. But wait a minute, we are dealing with probability vectors, right? Remember that we were dealing with probability vectors like 0.1, 0.3, whatever, 0.6, okay? So we are actually finding the deviation or the divergence between two probability vectors. So we want to give more weight for the options that are more probable to happen. Okay? So again, let's get rid of this. So what can we do over here? We can say, so we remember that we said that log 1, okay, log 1 minus log 2, right? Okay, and again, the second element comparison, log 1 minus log 2. Okay, and so on. And the third one is the same. And then we have added those up because we want to end up with a measure that estimates the difference between those two probabilities, right? Okay, so one more thing. We want to give more weight for the elements that are more probable in the first vector. Okay, so we will multiply this by the probability of the first, okay, or by the kind of like the first element, 1 times this. Okay, and the second element also was 1, right? Okay, and the third element was 1. Okay, so this ends up with this formula, which is kind of like if we have two vectors A, B, and we want to find the divergence between them, okay, we will multiply the first element of the first probability, okay, A of 1, for example, times the log of A of 1 over A of 2, or sorry, B of 1, okay, and the same, and then the same for A of 2 and B of 2, and the same for uh, A of 3 and B of 3, okay? So from this, we have understood the intuition. So because we want to give more weight, why did we multiply over here? Because we want to give more weight for the options that are more probable to happen, okay?
Okay, so hopefully we have understood where did this come from and why did we understood that the expectation of the log between those two quantities will equal the divergence right now between those two quantities over here. Very nice. So we have this divergence, which we have talked about, which is the path divergence between the, okay, assume that this is a Q, okay, between the, assume that this is a Q, okay, between the forward diffusion and the model probabilities. And we have understood that this is always greater than or equal to the negative log likelihood, right? Very nice. So we will do something to this right now, okay? Now, this divergence can be divided into two terms, which are the terminal divergence between, which is the divergence between the final point, okay, and the process divergence. Let me explain. Okay, so let me explain what we have done over here. You know, when we started the backward diffusion process towards time zero, what did we do? We started from a vector, right? Okay, which is it's let's call it p base. Okay, we started from a vector of probabilities over here, and then we have taken backward steps. Okay, until we got to time zero. Okay, so this was our starting point, and then there was a process that has gotten us back to time zero. Okay, so assume that. Okay, so assume that this is the model path. Okay, and assume that in the forward diffusion process we have this other path over here. So we say that the difference between the two paths is the difference between the starting point, which is the final vector at time t, okay, so we say plus the divergence between the two transitional processes over here, okay. Let me give you the intuition behind this. Let's say that we have two starting points. We have this starting point over here, and we have this starting point over here, okay. And from this starting point, we make this swing, for example, over here. Okay. And from this starting point, we make a different swing, for example, like this over here. Okay. So right now, we can say that the difference between the two lines will equal the difference between those two starting points plus the difference between the swings, right? Okay. So we can say again that the difference between those two lines will equal the difference between the starting points plus the difference between the swings. So this is what we have done over here. We said that the divergence between the two paths will equal the divergence between the vectors at time t, which is the final point, between the forward diffusion and the backward diffusion by the model, right? Plus the difference, the divergence between the two processes, which we will understand, which we will see that it will equal this formula over here. All right, so we have reached this inequality over here. Okay, So we have divided the divergence between the two paths into a divergence between the two processes plus a divergence between the starting points, as we have said over here. Okay? All right, very nice. So according to Radon-Nikodym formula, the divergence between two processes will equal this formula over here. Okay? So, according to this formula, the divergence between two processes, one is driven by Q bar and the other is driven by Q theta, okay, will equal this integration over here. Okay. Okay. Now, let me remind you of something, that the Q for the reverse process will equal the Q times the ratio, right? So what we will do over here is we will substitute for Qt by the Q times the probability generated from the forward diffusion path, okay? And we will substitute for the Q of the model by the Qt times the S, which is the probability ratio generated by the trained model, okay? So once you do those two substitution over here, you will end up, okay, you can do it yourself, it's very easy. Okay, so once you do those two substitution, you will end up with this formula over here. I have done it myself, it's very easy. Okay, so once you do those two substitutions, you will end up with this formula for the divergence between the two processes. Okay, which is exactly the formula present in the paper and the formula which you have actually asked about. So you will find that, okay, the full inequality will be, this one will be greater or equal than minus log p of x naught. Okay. Okay, and this will be also plus, this is the divergence process. Remaining is what is the divergence between the final vectors at time t, right? Which is dkl between blah and blah, as we said, right? Okay, which is also the final formula okay, in the paper. Okay, so we have finally arrived at this inequality and we have derived it from scratch. So let me show you the final shape in the paper, hopefully. Let me show you the final shape um, in the paper. Okay. Mm. This is the inequality. Okay, this is the divergence of the process, the process divergence, and this is the divergence between the probabilities at time t, right? Which is the starting point for the backward diffusion process. Okay, and it says that this part will equal this, okay, which is exactly what we have ended up with. Okay, so hopefully this answers this question over here, which is what's the intuition or what's the origin for those equations over here. So this is the inequality which we have right now explained, and this is the part which we have derived over here. Okay, and this is the same part, but maybe it's repeated over here. This is the same thing. Okay, so hopefully this answers this question for you. Now I want to move to the next question, which is this formula over here. Okay, so your question was, where did this formula come from? What's the intuition behind it? Okay, first of all, this is the backward diffusion formula. Okay, so this is how we get xt minus 1 from xt, right? Okay, so how did we come up with this formula over here? So our aim or target right now is to derive this formula over here.
First of all, we're going to have to look at this rule over here. It says the following. It says that the probability of x naught given xt will equal this shape over here. It will equal the probability of x naught times the probability of xt given x naught divided by the probability of xt. Okay? Now, let me remind you of something. Let's go to the paper. Okay, let me see if I can find this. Now, let me remind you of this equation over here. This represents the rate of change in the diffusion process, right? In the forward diffusion. Okay? It says that dpt over dt will equal qt times pt. Okay? So, the solution for this differential equation, if you try to solve this differential equation, you will get the following. You will get this. Okay? So, this is the solution to the differential equation. Okay, so based on solving this differential equation, we got pt will equal, okay, e to the exponent of tq times p naught. Okay, so based on the solution that we have talked about, we will get this equation over here. It will say that the probability of xt given x naught will equal this element of the matrix. So again, to make this clear, now the solution that we have talked about is actually a matrix. Okay, and it will be something like this: x naught, for example, x1, x2. Okay, for example, let's make it a 3 by 3 example, and here it will be x naught, x1, x2. Okay, and here we have those elements over here. Okay, now this element is, for example, the probability of x1 given x0. This element over here is the probability of x2, for example, given x1. Okay, this element is the probability of x1 or x node given x2, and so on and so forth. Okay, so this is why we say that the probability of xt given x node will equal this particular element from the matrix of the solution. Okay, all right, so we went forward right now and substituted for this part by this equation over here. Okay, one more thing. According to the solution that we have came up with, we know that p of x naught will equal this. We have substituted x naught into the solution of the differential equation. Okay, so we can also right now substitute for x naught by this as well. Okay. Okay, one last thing. What if we do the following? What if we came up with this equation over here and we say assume r of I will equal pt of I over pt of xt. So pt of I is the whole probability vector. Okay, assume that we have, for example, 3 words. So this is going to be point, for example, 0.1, 0.2, 0.3, whatever, or 0.7 or whatever. Okay, this is so pt of I is the whole probability vector, but pt of xt is just a number, a scalar. Okay, so what we have done over here is we have assumed r. We have came up with this variable. We said that assume r equal the whole probability vector divided by the probability vector of xt. Okay, so based on this assumption, pt will equal pt of xt times r. Okay, so right now we have substituted we have made this substitution over here. So we said that let's get this pt of xt. Oh, sorry. We said that let's get this pt and substitute pt of xt times r for it. Okay, so we will end up with this shape over here. Okay, once you get this shape and plug it into the equation above, over there, we'll come up with this function over here. I know this is a little bit tedious, but once you go through it, you will find it very easy mathematical steps. Okay, and eventually we ended up with this final shape or final equation which you have asked about in the WhatsApp conversation. Okay, so okay, yeah. So this is the final shape which we have seen over here. The most important thing is to understand what is this. This is the formula used in the backward diffusion process. Okay, so once you have the probability vector at time, okay, at time, for example, t, and you want to get back, you will use this formula to evaluate the next probability vector over here. Okay, very nice. Okay, so this is the formula that you actually have asked about. All right. All right. So the next question over here is the explanation or the intuitive explanation behind this formula over here. All right. In order to understand that, let me bring you back to this video over here. Let's see if we can do this. All right. So let me remind you, okay, of what we have over here. So this is the Q, which is the process of adding noise in the forward diffusion process, right? So we used to multiply this Q by the probability vector to get the probabilities at the next step. Okay. Now, now, what does the Q inverse mean? Let me remind you again, what does the Q inverse mean? The Q inverse is actually the matrix which, if you multiply by the same vector, okay, see here we're multiplying by the same vector, you will get the exact opposite vector over here. Okay, so over here, we multiplied the Q by this vector and we got this. Now, there is a certain matrix, which is the Q inverse, which if you multiply by this same vector, okay, you will get the exact opposite vector. So instead of minus 0.5, we got 0.5. Instead of minus 0.1, or 0.1, we got minus 0.1. Okay? Instead of 0.4, we got minus 0.4. Okay. So now the question is, what is this matrix? How can we evaluate this matrix? How can we get this matrix? Okay. So what should we multiply each element in this matrix in order to get this matrix? Okay, it turns out that we should multiply this. Okay, once you kind of like do the math, it turns out that you should multiply this element by 5/3, which is kind of like this over this, the ratio between those two. Okay, so when you multiply this element by the ratio between those two elements, okay, you get this element in the reverse matrix. Okay, and when you do the same for this one, but except for the ratio between this element and this element, you will get this element in this matrix. And the same thing for the rest of the elements in this matrix. So once you dive through the math, you will find out that when you multiply, when you do those kind of like multiplications, you will be able to evaluate this matrix. So this is what that equation, which you have asked about, is actually describing. So this is what this matrix is actually talking about. It says that in order to evaluate a particular element in the reversed matrix, you need to multiply that particular element in the forward matrix by a certain ratio in the probability vector. Okay, so this is what it actually means. All right. One more question might arise is that how did we derive this formula? How did we figure this out? How did we figure um, this formula out? The answer for that is very simple. The concept is very simple. We can assume variables over here, create a system of equations, and solve for that system of equations, and we will arrive at that formula. Okay, so I'll leave that for you. All right, so now the last question is about what about this formula over here? All right, so this is the formula that we use to evaluate the probabilities at the next step, right? So where did this come from? Let me remind you of this equation. If you remember that the rate of change is a problem. You know, the rate of change equals dp over dt, right? Which equals what? Q times p, right? Very nice. All right. Oh, that disappeared down. Okay, dp over dt equals qp. All right. Now, what if we create an Euler approximation for this equation, and instead of working on a very, very, very small dt, we say, delta p over delta t, okay, equals this right-hand side, qp, right? Very nice. What if I right now transition the delta t to the other side, so it will become delta p will equal, which is the change in the probability, will equal q times p times delta p, delta t. Okay. Now to make the approximation even more and more accurate, we can add higher order terms, right? But right now we will just work on our first order approximation for this ODE. So P mu will equal, this is the new P, new will equal the P old, right? Plus this Q delta T times the P old, right? This is what we have arrived at right now.
Right. Now, what if I factor P out, P old out? No. So I will get the identity plus Q times delta T. All right, so this is the probability of x naught or x old, let's call it, and this is the probability of x new. Okay, what if I want to find and evaluate the probability of x new given x old? Okay, given x old. This is what we're trying to evaluate. Okay, so what should I do in this case in order to get this? I should divide by the probability of x old, right? Because we know that the probability of x new, the probability of x new, or I call it p new, whatever, okay, will equal probability of x new given x old times the probability of x old, right? Multiplied by the probability of x old, or I call it here p old, okay? Normal probability multiplication, right? So in order to find this one, which is the final formula that we're trying to evaluate, we need to divide by this probability over here. So we will get rid of it. Okay, so we will be left out with this formula, which is the final formula that we have and you have asked about. Okay, and on the element level, this becomes the delta plus q times delta t. Okay, so this is the final formula that you have asked about.